G'day folks, welcome back to another lesson. Last we left off, we looked at projectile motion and learned how to describe it using the equations of motion. Today we're going to look into forces and how they influence motion. So without further ado, let's get into it. First things first, we need to identify what a force actually is. Now I have no doubt in my mind that if you look at any science textbook, you'll undoubtedly see something like a force is a vector measured in newtons and is a push or a pull. And even though that's technically correct, it seems to imply some sort of movement. And I remember having a hard time grasping this topic because I'd always think of force as something being applied to an object resulting in some sort of movement. Whereas this is not always the case. It certainly may be the case when there's only one force acting on an object, but it's not really a representation of the entire story. So let's do a quick thought experiment. Let's say we have a ball. So I'll draw a ball on the ground here. Say that's the ground and we've got a ball resting on it. What are the forces acting on this ball? Well, a lot of people will correctly point out that there is a force that's keeping the ball to the ground, and we can say that that's due to the Earth's gravitational field. But is that the only force acting on the ball? Well, it can't be, because if that was the only thing acting on the ball, then the ball would continue to move towards the center of the Earth. Similar to how if I threw a ball, so let's say I had a ball and I threw it and I imparted some force into it, it would keep moving in the direction I threw it in because there's nothing to stop it. In our case, however, the ball isn't moving, so it must mean one of two things. Either there are no forces acting on it, which can't be true because we've got the Earth's gravity acting downwards, which causes it to stay on the ground, or there's another force acting on the ball keeping it from moving. So we have to ask ourselves, where is this counterforce actually coming from? As it turns out, this counterforce is being applied by the ground back onto the ball, which I'll draw in as acting upwards. So the total forces acting on the ball will be the gravity and will be the normal force, so this is called the normal force, caused by the ground pushing back up on the ball. And because these forces will be equal in magnitude but in opposite directions, this ball will not experience any sort of movement. And you can think of this normal force as a push applied by the Earth onto the ball, and you can think of this gravitational force, which I will put down as W to signify our weight force, and that weight force will be a pull caused by the Earth onto the ball that we've got here. So let me label that so that we have that clear in our heads. So this is a push from ground, and we will have a pull in the opposite direction. We got pull caused by the Earth. So knowing what we know now, we can actually go back and come up with a definition of force that makes sense to us. And let's come up with our own definition of a force, which is that it's a vector quantity that can be thought of as a push or a pull that can bring about a change in an object's motion, but doesn't necessarily have to. Now, a force is measured in a unit called Newton. The SI unit for it is Newton, so I will mark this down. And because it's a vector quantity, it will require a direction and a magnitude. So let's go back to our ball scenario where we had the ball resting on the ground. So I'll draw that back in. And I remember the ball was pink and it had a weight force that was pushing down, acting down as a result of the Earth pulling on the ball. And that weight force would be the mass of the ball multiplied by the gravitational field, which we'll go through in a bit as well. And we'd have a normal force due to the Earth pushing back, or the ground pushing back on the ball itself. So we have a normal force. Now let's say somebody came along and actually kicked this ball. So let's say we applied a force to it and kicked it. So we'll call this force the kick force. We'll say force of kicking. What would we expect to happen to the ball? Well, we'd expect the ball to start moving. And not only would the ball move, it would move in the direction of the applied force. And this actually brings us to Newton's first law, which is also known as the law of inertia. And you might have heard of this Newton guy before. He seems to be pretty famous. And the law of inertia states that an object will continue to be at rest or continue with a constant velocity unless it experiences an unbalance in forces. So going back to our ball, there was an unbalanced force introduced to the ball, therefore causing the ball to accelerate in the direction of the force. Let's consider another scenario. Let's say we have some car that's traveling on a road, so let's draw that car out. Let's say this car here is on a road, and let's say this car is moving at a constant velocity, so we'll just call that some x meters per second. Now there's movement occurring in this situation, but does that mean there's an unbalance of forces? Well, no, because this velocity is constant, so it must mean that there's a balance of forces occurring. So let's look at all the forces acting on this car. As we know from before, there's a weight force that's pulling the car towards the ground. There's a normal force due to the ground pushing back up on the car. There must be some driving force that's causing the car to move. But because this is a constant velocity situation, there must be a frictional force that's equal to the driving force, because this car isn't experiencing any acceleration. So I'll draw that frictional force as green. So if the driving force was to be, let's say, 3,000 Newton, and this car was going at a constant velocity, that means there would be no acceleration occurring. The frictional force would also be 3,000 Newton in the opposite direction. So if an object remains stationary or at a constant velocity without the presence of an unbalanced force, it must mean that an unbalanced force would cause the object to experience a change in its velocity whilst that force is being applied. And this brings us to Newton's second law, which says that the acceleration that a body experiences as a result of an unbalanced force is directly proportional to the mass of the body, which can be written as F is equal to ma. And this is Newton's second law, so I'll just write that down for reference. Law. Where m is the mass of the object, so that's mass. A is the acceleration that's experienced by the object. And F is the sum of all the forces that are acting on the object. It is important to remember that acceleration and force occur in the exact same direction. So going back to our ball example, we had the ball, we had the weight force caused by gravity, we had the normal force caused by the ground pushing up on the ball, and we had this unbalanced force caused by the kick. We have a balance in this direction because the weight force will be equal to the normal force, so there won't be any acceleration occurring in the up or down direction. However, in the left and right direction, we will have an unbalance of force caused by this kick, so this ball will accelerate towards the right. So let's put some numbers to this scenario. Let's say we wanted to find out the acceleration of the ball, given that the ball has a mass of 300 grams and our kicking force equals 30 newtons. Well, given that we know that the mass is equal to 0.3 kilograms and the force, or the kicking force, is equal to 30 newtons, we can go ahead and apply Newton's second law, which is the sum of all the forces equals mass times acceleration. Our mass here is 0.3 kilograms. Our acceleration is what we want to find, and our force is equal to 30 Newton. And if we put this in the calculator, we get an acceleration of 30 divided by 0.3 newtons per kilogram, which is equal to 100 Newton per kilogram. And if we think about this a little bit more, the units start to make more sense. And that's because acceleration is just force divided by a mass. So if a ball had more mass, let's say 600 grams, then the acceleration that it would experience would be half as much. And that's because there'd be twice as much mass required to accelerate. Now when we kick the ball, we apply a force to the ball, but we also feel a force pushing back on us, which actually brings me to Newton's third law, which states that if object A, so say we have an object, exerts a force onto object B, so we can call that FAB, then object B also exerts an equal and opposite force back onto object A, which I will call FB on A. And I can write that mathematically as FAB is equal to the negative of FB on A. And this here is known as Newton's third law. So this is the third law. Now, why is it that if both objects are experiencing a force in the opposite direction, that the ball accelerates so much more than the leg? Well, this is actually explained by Newton's second law, because we learnt that the acceleration of the body experiencing the unbalanced force would be proportional to the mass of that body. So a mass of a leg, or mass of the kicker, would be, say, 80 kilograms. So let's say mass of the kicker, so call that MS, is equal to 80 kilograms. And the force experienced by the kicker would be opposite to the force felt by the ball. So the force on the kicker would be 30 newtons towards the left, so 30 newtons to the left. And if we applied Newton's second law equation, so force is equal to mass times acceleration, where mass is 80 kilograms and the force is 30 newtons to the left, then we'd go 30 is equal to 80 divided by A, and our acceleration would be 30 divided by 80, which is equal to 0.375 meters per second squared, which would be tiny in comparison to the acceleration felt by our ball. And remember, because this force is acting in the opposite direction, this acceleration would be towards the left. So that brings us to the close of this lesson. I hope you leave knowing a little bit more than you did before. And as always, I'll catch you at the next one.